So the idea of the method of variation of parameters is that if I have a linear nth order non-homogeneous differential equation and in this case, we're not going to assume that the coefficients are constants. So we have something like y, the nth derivative of y, plus p1 t times the n minus first derivative of y, plus yada, 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 plus some polynomial n minus 1 of t, y prime of t, plus some polynomial some function of t, y equals some other function of t, g of t. Okay, so again, this is a linear differential equation because we have these kind of nth derivatives of y going along here, and then these things here are functions of I said polynomials earlier. They don't have to be polynomials. Any kind of functions of t will work, and then of course g of t also is a function of t. So you just have these functions of t in front of these derivatives of y. And in this case, we're not assuming that those are constants, which is what we'd been assuming earlier. So this is a more general result. So what does a solution of this kind of thing look like? Well, it's going to look like the solution will, again, have two parts. So it's going to have yc of t plus yp of t. Okay? And so for this method of variation of parameters, we're going to assume that we already know this. And that yc of t is equal to some thing like this. So it's like going to be c1 y1 of t plus c2 y2 of t plus blah 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 plus cn yn of t. So we're assuming that we already know the solution to the corresponding homogeneous differential equation. So we're assuming that we already know the solution to the corresponding homogeneous differential equation. What do we mean by that? The corresponding homogeneous differential equation is the same on the left-hand side of the original differential equation, but the g of t is 0. Okay, so that's the corresponding homogeneous differential equation. So we're assuming that we already know the solution to that. Now that's a huge assumption. So I'll just kind of say in parentheses, this is a big assumption. Assumption, T-I-O-N. Anyway, this is a big assumption because these yj's it can be really, really hard to find these solutions when these functions of t up here in our original differential equations are not constants. It's really hard to find a solution. Anyway, we're going to start from assuming that we already know yc of t, and we're going to be able to use the solution that we have for yc of t to find the particular part of the solution. So basically, so the method of variation of parameters, we're going to use what we know about yc of t to find yp of t. Okay, So that's the method of variation of parameters. And the solution here is going to depend on something that we called the Wronskian, which we did before. So we'll use W of t to mean the Wronskian of the yj of t's, which are these functions up here that are the pieces of the the yj of t functions that are the pieces of the complementary solution. And we'll use this notation Wm of t to mean the determinant obtained by replacing the mth row the mth column with this column vector 0, 0, 0, 1. So all zeros and then a 1 at the bottom. Okay, so that seems a little weird, but I'll show you what I mean by that in just a minute. So then the particular solution is given by this thing, yp of t, that's the second half of the solution that we're looking for, is equal to the sum m equal 1 to n of ym of t, that's the piece of it, this mth piece from up here, times the integral from t naught to t Okay, I think something funny happened in my video. Anyway, so this g of s here is given by the right-hand side of our original differential equation up there. And then the w of s, that's the Wronskian with the mth row replaced by that column. And then this w of s, that's just the Wronskian, the regular old Wronskian of those yj's that I was given. And you might be wondering, what's the deal with the s? Well, the s is just really a dummy variable. Once I integrate and I'm going to plug in the t's, I'm going to end up with a function of t in the end. And I'm going to sum that all up. Okay, so I will show you an example on the next slide that may clarify some things here. All right, here's an example. So we have this homogeneous differential equation, y triple prime minus y double prime minus y prime plus y equals, and this is just some g of t that I'm not given. Okay. And I'm going to assume that I'm going to be given that y1 of t, which is e to the t, y2 of t, which is t e to the t, and y3 of t, which is e to the negative t, are solutions of that homogeneous differential equation. Non-homogeneous. Oh yeah, no, solutions to the corresponding homogeneous differential equations. In other words, I'm saying that yc of t is equal to c1 e to the t plus c2 t e to the t plus c3 e to the negative t, right? That's what we're saying. That's what that means there. Okay. All right, so I have my corresponding part of the solution. Now I want to find the particular part of the solution. Okay, so we're going to use the method of variation of parameters. Okay, so let's see if we can find what W of S is equal to. Well, let's find W of T. So this is just going to be the Wronskian of those three functions. So it's going to end up being a 3 by 3 matrix. And so I'm going to put e to the t here, and then I'll put t e to the t here, and then I'll put e to the minus t there. Now to compute this Wronskian, I have my three functions there, and I'm just going to do the first derivative on the next row and the second derivative on the third row. So I take the derivative of e to the t, this is an easy one, I get e to the t, and then the derivative again, I get e to the t. Okay. And how about e to the negative t? The derivative of e to the negative t is negative e to the negative t, and the derivative of negative e to the negative t is negative e to the negative t, so I get positive e to the negative t. Okay. This one I'm going to have to do using product rule. I'm just going to write it in simplified form. You're going to get t plus 1, e to the t. Take the derivative again, you're going to end up with t plus 2, e to the t. Go ahead and verify that for yourself. I just went ahead and wrote the simplified form here just so it didn't take up too much space in my matrix. All right, so now I want to take the determinant of that, and if you go back and review how to take the determinant of a 3 by 3 matrix, you want to, go back and review how to take the determinant of a 3 by 3 matrix, but I'm just going to tell you, when you compute this determinant, simplify it all down, you're going to get 4e to the t. Okay? Now we want to find W1 of t. Well, what's that going to be? Well, that's going to be the determinant of, I'm going to rewrite that Wronskian matrix, except in the first column, I'm going to write the 0, 0, 1 there. Okay, so the rest of it's going to be the same. T e to the t, t plus 1 e to the t, t plus 2 e to the t, e to the negative t, negative e to the negative t, and e to the negative t. Okay, so when I compute this determinant of this 3 by 3, I'm going to end up with negative 2t minus 1. When you compute that determinant, simplify it down, you'll get that. Okay, so what is W2 of t? Again, it's going to be that same determinant, except in the second column, I'm going to write 0, 0, 1. Okay, the rest of that stuff I'm just going to recopy. E to the t, e to the t, e to the t, e to the negative t, negative e to the negative t, and e to the negative t. Okay, so I compute that determinant, and you end up with, you actually end up with 2. Okay, well, anyway, you compute the determinant, you simplify it down, you end up with 2. And W3 of t is going to be this same determinant again, but in the third column, I'm going to put the 0, 0, 1. Okay, so I'm going to have e to the t, e to the t, e to the t, and then I'll have t e to the t, and t plus 1 e to the t, and t plus 2 e to the t. All right, so you go ahead and do all of that, compute that determinant, and you'll end up with, after you simplify, e to the 2t. All right, so now I'm ready to plug it all into my particular solution. So I'll do yp of t is equal to, okay, so the first thing I want to do is I want to do my y1 of t. So what is y1 of t? y1 of t is e to the t. And then I want to do that times the integral from t naught to t. I wasn't told what t naught was, but anyway, we'll just write it out like this. Of, what is my g of s? G of s, I wasn't given a g of s, it was just that. But say if you had a function there, you'd plug it in. So we'll just say g of s here. Okay. And then I want to do w sub 1 of s. So that would be this guy with s plugged in. So I'll have negative 2s minus 1 over w of t, or w, just regular w of s. So I'll have 4e to the s ds plus. Now I want to do my y2 of t, which is up here, so that's t e to the t, times the integral of from t naught to t, and if I were given a t naught, I could actually compute this integral. I have g of s, again, g of s, so whatever that g is up here, you'd plug in s to that, and then I'll have w2, which I computed to be 2, over the Wronskian, which was 4e to the s ds, so I can compute that integral. If I knew what the g was, I could compute that. And then I'm going to do plus, and this is my last term in this sum here. So my last one is going to be y3, so that's e to the negative t, times the integral from t naught to t of g of s, again, I don't know what that is, but if I were given it, I could plug it in there, times w3 of t, which was e to the 2t, over the Wronskian, which was, it should have been w3 of s, so e to the 2s. Okay, that's an s right there. Okay, good. And then over w of s, which is 4e to the s. Okay, so that is the particular solution. Okay, and so if I was asked to write out the whole solution, it would be y is going to be equal to the yc of t plus the yp of t. So the yc of t is just those constants times that, this thing here, those constants times those yj's, right? And then yp of t is going to be this thing. So if I had an actual g of s and I knew what t naught was, I could maybe compute those integrals and come up with something a little bit cleaner than what I have here. Okay?